Yeah, okay, yeah, that's good. If you are planning to fall asleep though, then do so after this slide, because this is the most important one. This is a list of things I've recently worked on. And in general, if you care about anything related to algorithms, data structures, in particular lower bounds, or any type of question in combinatorics or graph theory that even can be slightly motivated by theoretical computer science, I would be very happy to talk to you. If you don't care about these things, I would still be quite happy to talk to you. Okay, so for this talk, I'm going to talk about a recent result. As I said, I do not assume any prior knowledge about anything, and this actually can even be phrased as kind of a riddle. So yeah, hopefully we can survive that, and then we go on and are done with these talks. So I have some biased coin. This means that one of the side of the coin has probability f plus beta for some biased beta to show up, and the other side has probability f minus beta. And we do not really need to assume that, but let's even assume that I tell you the magnitude of beta, but I do not tell you to which direction do I have this bias. So we can even phrase it a bit more simply by I have a biased coin. There is some positive bias beta that you even know of, but you don't know if it's the heads that have probability f plus beta to show up or the tails that have probability f plus beta to show up, and you would want to distinguish between these two cases. So in what way? I'm going to give you n coin tosses that are completely independent from each other. And your objective is going to be to tell me the direction of the bias with probability that is, let's say, larger than 2/3. And this is a very natural question in statistics and in many other things. For example, in Pei's talk, in the first talk in this session, someone from the audience asked about how important is the third and things like that. So in general, this is the question of, if I can generate some small bias, how much can I amplify it? What can I do by looking at repetitions in order to have a larger constant bias? And obviously this can be amplified as well. And also it appears very naturally in streaming lower bounds, pseudo-randomness, things like circuit complexity, and more. And as you can imagine, we are going to think of beta as some function of n is the number of coins we are getting, and the problem is going to get much more difficult as beta is getting smaller. If the bias is smaller in comparison to the number of coins, this is more difficult. And actually, if beta is much smaller than 1/√n, this is even unsolvable, because statistically, if the bias is much smaller than the standard deviation, there is nothing you can do about it. But what would you suggest doing in general? How would you tell me the side of the bias? Yeah, that was a real question.
Count and see which comes.
Exactly. There's like one trivial thing to do, which is to look at the majority. If most of the coins are in one side, then probably the bias in that side. And in fact, it's quite easy to show that this is the best you can do statistically. There's nothing better to do than just to look at the most of the coins and say, yeah, this is the side of the bias. This would give you a constant advantage if beta is of the magnitude of 1/√n. And as we said, if it is much smaller, you can't do anything. If it is much larger, then actually your error probability is going to be vanishing. Then is that it? Is that all we are going to talk about? Unfortunately, we need like 10 more minutes. But the reason for that is that in order to be able to tell what the majority of the coins are, I need to be able to count. But in many very natural and very important models of computation, we are not able to count. So what we are going to need to discuss models of computations in which counting is hard or even impossible sometimes. This is a list of maybe the most well-known such models. If you do not know these names, don't worry. I will mention very briefly the ones that we are not going to deeply discuss, and I will mention, obviously, to a deeper extent, things I am going to discuss more. So whoever doesn't know what AC0 is, never mind. Whoever do know, I will remind you that the seminal result of Rasborov from 85 showed that majority is not computable in AC0. So for this model of short depth circuits, you cannot compute the majority. This is one example of these things. And an example we are going to discuss a bit more, and maybe is somewhat more natural for people who didn't see this type of computational models, is just formulas, Boolean formulas. What is a Boolean formula? This is just a bunch of Boolean variables separated with AND gates, parentheses, OR gates, negation gates. You can also think of this as a circuit, but a circuit that is a tree. I can't use the same output in two places because then I wouldn't be able to write it as a formula, but I can write it in this way. And because I can write it in this way, there is also a notion of depth of a circuit. So there is the size of the circuit, how many gates I needed, and also the depth, which is the depth of this tree, or if you think only at the formula itself, it's the amount of open parentheses I might have at the same time point. So another seminal result of Valiant from 84 is that you can compute the majority with this type of formula that has polynomial size and only logarithmic depth. So this was somewhat surprising, but it does show that using this model of computation, you are able to compute a majority. But something that is a bit more restricted that we are going to consider is something called read-once Boolean formulas. So what are read-once Boolean formulas? So these are still Boolean formulas, but now every variable can appear only once. So I want my formula to have every variable appearing only in one place. This means that basically when I compute it, I can't go back to previous variables and things like that. And the same construction of Valiant showed that if we would want to take this construction and to use it in order to solve this coin problem, so we have n variables that appear only once, we just put our coin tosses in these variables, then if the bias is larger than this thing, n to the minus 0.306, then we would be able to detect the bias. So we constructed some formula with n variables and low depth, such that if you would put in every variable which appears only once a random coin toss with bias larger than this, then the output of the entire formula is going to be constantly biased towards the right direction. And in fact, it was shown by Dubinel at Zwick about a decade later that this is tight. There is no read-once Boolean formula that can amplify more bias than that to a constant bias. So this is the best you can do with Boolean formulas. And we will back to that in a bit. We are just going to define another model. This is the last one. This model is basically going to be something that is equivalent to computation with limited memory. So this is called a branching program. What is a branching program? We have some directed graph that is separated to layer, and from every node we have two edges to the next layer that are marked by 0 and 1, and every layer is associated with some input variable. And this defines a way to compute things, right? Because we are going to start at some node, and at every point we are going to check the value of the variable associated with this layer, and according to the value of this input variable, we will go to some node in the next layer. So the width of a branching program is how many nodes I might have at the same layer. This corresponds to how many states I have in my memory. And the number of layers is the length of this branching program. And for example, if you want to compute functions like AND or parity, you can very easily do it with width only 2. You need only 2 states and length n. Just remember the parity, remember the AND using your two states. And another result that is very important in this field, which is a result of Barrington from 89, is that if you have a circuit with short depth, you can translate it to a branching program with a very low very low width. So, for example, if we take the construction from the previous slides of majority with a length poly-n that add depth only logarithmic, then this actually turns into a branching program that computes the majority with width 5. Yeah, so actually this 5 is inherent. It's a really nice proof. It's not complicated. This 5 actually comes from non-solvability of S5. So it was something cool happening there. But then again, we might think of the model of read-once branching programs. So this is the same thing, but now each variable can appear only in one layer. And this is now equivalent to what I mentioned earlier, which is basically saying that I compute with limited memory. So this is completely equivalent to saying that I get the coins one by one, I get the coin tosses one by one, but I have only m bits of memory. I have only width states I can go between, but there is something to notice, which is that we have a clock. In what sense? Different layers may do different things with the memory they have and the new coin toss they are getting. We don't have to do the exact same thing with the memory and the coin in every time. So I can look at the time when I get a bit. And actually, if I couldn't do it, this would simply be an automata with the width number of states. Then this is actually quite bad in order to distinguish bias. So it was showed in the early 70s that if I have an automata with W states, then I cannot solve the coin problem. I cannot distinguish bias that is less than 1 over W, less than 1 over the number of states. So for example, if I have only a constant sized memory, I will not be able to amplify more than a constant bias. But what we are going to see now is that when I do have this clock, I can actually amplify 1 over log n, or in general, 1 over polylog type of bias with only constant number of bits, only constant sized memory. And why is that? So again, we talked about these read-once Boolean formulas. Look at this formula I have here. It's called the tribe formula. So basically, I have OR gates between tribes where each tribe is an AND gate of S variables. What can I do with that? So for example, if my bias is something like 1 over log n, and I take the size of the tribes to be something like log n, then each tribe is going to be 1 with probability that is roughly E over the number of tribes if the bias is in that direction, or 1 over E over the number of tribes if the bias is in the other direction. So when I would take the OR of all of the tribes, in expectation, I would see either E or 1 over E tribes that are 1, which would give me a constant separation between the probabilities of having 1 in this case and 1 in this case. And the reason that this is a very shallow Boolean formula. This is of depth only 2, right? We don't need more parentheses than just this. Then the reason that we have a very low width read-once branching program out of this is just that we can translate this formula into a branching program. I need 1 bit of memory to remember my state within the current tribe. I will just say, I got a new bit. I see in my watch that I'm still within the tribe. Let's just end it to this bit. I see in my clock that I'm still in this tribe. I will just end this to this bit. And whenever I will see that I'm out of a tribe, I would need just another bit of memory to add, to like OR these two, basically. To add these two, and in the end, I will know the value of this formula. And actually, in general, if I have a formula of depth D, I need only something like these states of memory, not even D bits. So I need only log D bits of memory in order to emulate the formula of depth D. Okay, so now back to the coin problem and what we know about it. So as we said, we need only constant size memory if the bias is something like 1 over a polylog. And in fact, doing something similar, as we said, we can emulate the short depth Boolean formulas all the way up to this and to the minus 0.306, because in that regime, we still have this construction of a shallow formula. And this is, again, the upper bound is by this valiant construction. Brody and Verbin in 2010 showed also a matching lower bound of log to the 1 over beta in this form. The reason I drew log in such an ugly manner is that in the polynomial regime, when beta is polynomially small, this is basically log. Right, so if beta is polynomially small but larger than this thing, then you need log n bits, and this is tight in this regime. Something that is quite recent by Braverman, Garg, and Woodruff from just a year ago is that majority does need a logarithmic amount of bits. If you want to exactly compute majority, you do need to count, you need to have the memory to count. And they also showed, and this is not difficult, that if beta is very, very small, if it is smaller than a small constant over root n, the two problems are equivalent. If I want to solve the coin problem where beta is almost the standard deviation, I need to be able to do majority, and then I need to be able to count. Then I need this logarithmic number of bits. And then the question is, what's happening in between? Because there are good reasons to believe in each of these sides. I'll just remind you that one good reason to believe that this side is the correct one is that we know that we don't have Boolean, read once Boolean formulas better than that. There is a lower bound showing that this is the best you can do with a low depth read once Boolean formula, and the construction of the upper bound is just emulating that. A reason to think that maybe here we should have some threshold is that it could be that majority is very difficult because you actually need to count, but if you have some slack, then you can suddenly do much better because you don't need to explicitly count. So in very recent work with Mark Braverman and Sumega Garg, we show that in fact neither of the bounds are true, and the correct bound is n to the minus third. So basically, if the bias is smaller than n to the minus third, you must count, you must have enough memory to remember how many heads you saw. But if the bias is slightly larger than that, then already you need only exponentially less memory. You need only log n bits and not log n bits. And I think we started a bit late, so we have like a couple of minutes to say just like one slide about the proof. Don't worry, it's not going to be long. I will just say that both things are somewhat surprising. Like this is surprising because it shows that branching programs are actually better than these formulas. We didn't know if they are equivalent or not in this sense. The lower bound is surprising because for information theoretical arguments, you couldn't get better than 1 over square root n. You have more information than you need, so this is kind of dragging it further than the information theoretic lower bound. Okay, and now I will try to give you one slide about why n to the minus third. Why did this thing come up? So I'm going to say that a sequence of integers is k universal for our purposes. If for a simple random walk that I stop when it goes past k or minus k, so I'm just doing a simple random walk on the line and I stop it whenever I reach k or minus k, this random walk is going to have large probability, let's say at least 90%, of being a subset of this sequence. So a sequence is universal if it is very likely that a random walk that I stop whenever I reach this k boundary is a subset of it. So I would call this a universal sequence for k, and trivially there are universal sequences of size kq. Why? Just take the entire range of minus k to k and duplicate it k squared times. And the random walk should pass k after k squared times. So yeah, you should be able to, like if I take a random walk of this length, I am going to pass k or minus k. So it is very likely that the size of my random walk, if I stop it at this point, will be at most that, and this means that it will be a subset of this thing. So basically what we show is first that this is the best you can do. There is no universal sequence better than that. And the second, which is the maybe somewhat surprising thing, that any read once branching program must induce this type of universal sequence for k that is roughly 1 over beta. Yeah, and I don't think I have time to explain why this is true, but this obviously gives this bound. It shows that the total number of states you are going to see is at least this 1 over beta. Okay, thank you very much.
Any questions for the speaker?
Yes.
So this intuition at the end, was this known before your result, or so like what you just sketched disprove? That's like this.
No, so like both of these things were not known before.
The exponent was also not expected.
No, so like the two sides were somewhat the more likely things because, as I said, there were good reasons for them. Yeah. Yes.
What's the intuition for this log root 5 minus 1?
Okay.
As being exact, could you say something about that?
Yes. So in general, it is something of the following form. If you would take biased random bits that are independent, and you'd try to amplify the bias by doing something that is similar to what we showed earlier. Take like the end of 2 of them, the end of 2 of them, and then the OR of these two things. Then this thing is going to amplify it, take some bias and change it to a different bias. So the stable point of where this bias is being taken to is exactly this thing. So this is the bias that will return to the same bias by this simple construction.
No other questions?